Hey, good afternoon, good evening to some of you. My name is Greg Johnson. I will be the moderator for this session. The topic is oil analysis limitations, and our presenter is Evan Zabawski from TestOil, coming to you from Canada. I had the pleasure of introducing Evan last year at this event. I'd like to welcome you back. Appreciate you coming back this year. Before I hand it off to Evan, I'd like to remind everybody we have the Play to Win game. Down in the left-hand column there, you'll see the code for this particular session. Go back to the home page and enter that code in the Play to Win link. And the more code you put in, the better chance you have of winning. There's some really nice gifts, some iPads, iPads, Apple Watches, and some earbuds. So good luck to everybody for that. If you have any questions, please use the chat function. We'll have a question and answer session at the end of the presentation. And with that, I will hand it over to Evan.
Great, thank you. So yes, today's presentation is called Oil Analysis Limitations, or as I said, sometimes people say, why do my results not correlate? So that's kind of your secondary title there. I am the Senior Technical Advisor here at TestOil. So my role generally is doing training. So this is right up my alley to give you a presentation on this. I could give a short answer as to oil analysis limitations, and basically it would be this, that when you consider any limitation to a test, it's what does it cover? What's the test selection? And basically oil analysis can be broken down into three categories. So there's basically physical and chemical properties, which you would call fluid properties. There are contaminant tests, and there are wear-related tests. And the simple point is that most tests only fit in one of those three categories. You'll notice a couple down in the bottom right fit into two categories, and one right across the top fits in all three. But the short answer to why do my results not correlate is they're often not measuring quite the same thing. And when seen this way, it's pretty easy to see that, yes, some tests are measuring something that are not being measured by a different test. But what if they're both in the same category? So let's focus this presentation on two of them. Let's take a look at elemental spectroscopy, or what most people call the wear metals test, and particle counting, and figure out why those two don't always correlate the way you think they should. And again, I could give you a pretty short answer on why that is, but it's better if I explain it in a bit more detail. So to do that, I'm going to walk you through both of the tests and give you some background as to, how the tests are done, and you'll come to your own conclusion, hopefully, as to why they don't always correlate. And then we'll discuss that correlation at the very, very end as to what that actually does or does not tell you. So with that in mind, let's start with the first of those two tests, elemental spectroscopy. So basically pulling right from ASTM, what's the scope of this test? Well, it is meant to measure wear metals, additives, and contaminants. Well, what's the significance of measuring those three things? Well, and this is the probably one of the most not known things about the test is that when we're measuring wear metals, obviously you're checking for signs of wear, and when we're measuring for contaminants, we're probably assuming that those contaminants will lead to more wear. But the part that's not as well known is how or why are we measuring additives? A lot of people misinterpret this test to assume that we're measuring additives as a way of determining, say, additive depletion or breakdown or something along those lines. But ultimately, we're barely scratching the surface at additive presence, because essentially with this test, all we're doing is confirming that the building blocks of the additives are present, and therefore the assumption is it's just the right oil. And that's about as far as we can take the interpretation of additives being measured by elemental spectroscopy. But allow me to explain further, and you'll come to understand what I mean by this. So first and foremost, what's the principle of this test? How do we do the test? So the basic principle is this. We take your sample, we dilute it with a solvent, and then we introduce that solvent as an aerosol. So imagine that, small, tiny droplets of your sample, diluted, into the base of this plasma that you see pictured here. So what happens is when your sample enters this plasma, which sits at around 10,000 degrees Kelvin, so as hot as the surface of the sun the sample will ionize. Now, what that means is a bit detailed, but for lack of a better word, think of it like burning. And essentially, during an ionization, an atomic emission is given off. So again, keeping it in simple wording, light is given off. And the idea is that all we're actually measuring is light. So the sample's introduced, it ionizes, and here's the cool part. Every element on the periodic table ionizes differently, gives off a different atomic emission, and therefore we can measure these atomic emissions, and by the wavelength, we can determine what element is there. And I keep emphasizing the word element because it is the name of the test, elemental spectroscopy, but it's also to illustrate the point that we're only measuring the elements, not the chemicals, not the compounds, not the alloys. What I mean by this is that if you had a sample, had say some Babbitt bearing wear in your oil sample, this test wouldn't tell you had Babbitt. It would say you had lead and you had tin. Now, if you had a sample that had, say, a bronze or a brass piece to it, whether that be a gear or a wear plate or something like that, again, it wouldn't say that you had brass or bronze particles. It would say that you had lead and tin particles because that's one of the primary metals in brass and bronze is both lead and tin, but also copper. So when we see just lead and tin, we don't know that it's brass or bronze. We assume it's something more like Babbitt, but as soon as we see the presence of copper, we can infer that that combination would represent something like brass or bronze. So that's kind of my point, is that we're only seeing the elements. We're seeing the building blocks. We don't see what, like I said, what the chemical or the compound or the alloy of the metal might be. So therefore, when we measure your additives, again, we're not seeing that there's an antioxidant present, or we're seeing that there's an anti-wear additive present. We're seeing something like calcium is present, or phosphorus is present, or zinc is present. And we have to infer from the combination of those elements what additive or additive package we feel is present in the oil. And it doesn't really mean that it's working. It just means that it's there. So elemental concentration is a key takeaway to understand what is this actually measuring. Now, just to give you an idea, so you can picture this a little bit better, this is kind of what the optical side of the instrument would see from that plasma. And I've given you three different metals that, by visual appearance alone would appear very, very similar: aluminum, tin, and lead. And what you can see is that as they ionize, the atomic emission that's given off by each of those individual elements is drastically different from the other. And that's what we're actually measuring, to measure the elemental concentration. Now, why I'm mentioning all this, why I'm going into this amount of detail, is you have to understand something very fundamental about this test. And the point is that as we introduce your sample, it's introduced as an aerosol. So it has to be rendered into very small droplets before it gets placed into the plasma. And that size limitation of the droplets leads to a very important realization about this test. And that is that this test is really only measuring accurately measuring in the 0 to 5 micron range. Anything above 5 microns to approximately 10 microns is measured with less accuracy, meaning we're not as precise about particles in that range. And pretty much anything larger than about 10 microns is not measured at all by this instrument. And the quick analogy I have for you to help you understand this is, think of it this way. Imagine you were measuring meteors, shooting stars in the night sky. How would you measure them? Well, you and me, just with the tools we have, could use a stopwatch to do that. We could time how long they take to burn up across the atmosphere. Now, when we gather our data about a series of meteors that have streaked across the sky, how would we know which ones were the smallest and which ones were the largest? Well, the ones that took the most time would be larger than the ones that took the least time, would be a pretty safe assumption, because the bigger they are, the longer they take to burn up. But imagine now we are performing these measurements through a skylight. Perhaps you have a skylight in your home, and imagine that you're staring, standing in whatever part of your house has a skylight, and you're looking straight up into the night sky and looking at the shooting stars as they go by. How many large meteors do you think you can measure, or count even, going past your skylight? Well, right away you should understand that you're only seeing a portion of the night sky, and therefore you're not necessarily going to see all the particles. But because of the limited window that you're seeing, even if a large meteor were to go by right where you could see it, how do you know it's large? You didn't see it when it began streaking across the sky, and you might not be able to see it as it finishes streaking across the sky. You saw that meteor as it went past the window. So in your mind, based on your observation, all you can do is count it as a small meteor. Well, that same analogy holds up with elemental spectroscopy. Every element that ionizes in the plasma is basically a shooting star. It's giving off light. And we're only looking at a portion of the plasma. So if it's a particularly large particle, it may not even be suspended in the aerosol and may not even enter the plasma. But if it is small enough to be suspended in the aerosol, it may not ionize completely within that plasma. So long story short, this test measures very, very small particles. Under 5 micron particles are generally where it's targeting. Now, for a lot of people, they think, wow, that's pretty limiting. That doesn't really give me a lot of information. Actually, it does. Because think about this. What does it measure again? Wear metals, additives, and contaminants. Well, wear metals should be at or below clearance sizes. And most clearances, dynamic clearances, are generally under 5 microns. The contaminants that we're most concerned about causing that wear also would have to be near clearance sizes, which again would be under 5 microns. The additives are on a nanoscale, so they're generally an order of 1,000 times smaller than 1 micron. So yes, they're all measured. So that 0 to 5 range, as limiting as it sounds, is actually not a very bad thing. The problem is, and that's why you can see the image I've chosen here, is that if the particles are big enough that you can see them, that the human eye can detect them, like in this sample that you see here, this instrument won't measure those. They may not even be introduced into the plasma, and even if they are, they will not ionize in a way that represents how big they truly are. So with that, understand how this test works. Now, just to give you a graphical representation, yes, this test is very, very accurate between 0 and about 5 microns. Around 5 microns, as I always say, it takes a nosedive on accuracy, and around 10 microns, it pretty much gives up the ghost, and particles cannot be analyzed. Thankfully, there's a handoff to other large particle analysis like analytical ferrography, wear particle concentration. Even a simple patch test could pick up on some of these particles. But we next need to talk about particle counting. So let me finish this test off and we'll get to there. So my point is, if we're discussing elemental spectroscopy, there are some interferences to this test. So number one is that we do have to dilute your sample to turn it into an aerosol. Well, what if it doesn't dissolve in the diluent, right? The solvent that we're using. So sometimes we have to change up the solvent, and that can affect the accuracy of the test because it's not been calibrated or set up for that particular solvent. But another one is water. Water will cause that plasma to sputter. Water does ionize, right? We'll see it, but it causes the plasma to sputter. So now if the plasma is wiggling, imagine how much harder it is for us to get an accurate measurement. But the joke I always make about this is if you've got so much water in your sample that we can't get an accurate elemental spectroscopy, there's your problem. High water content. Don't worry about what your wear metals are doing until you get rid of the water. But another quick comment here about elemental spectroscopy is what are the limitations to this test. So already having seen these, I can summarize it as this. Remember, we're measuring elements, not chemicals, not compounds, not alloys. We're only measuring the really, really small particles. We're not really measuring anything large. So what that means is that if we did have very severe wear or very severe contamination, this test might not tell us anything along those lines, might not give you the slightest clue that that is happening. So that's elemental spectroscopy. Let's talk about particle counting. Now, I will discuss particle counting 2 different ways here real quick. So first and foremost, the way most people are familiar with is called optical particle counting. And the scope of that test, again, straight from ASTM, says it's meant to identify the size and distribution, the quantity of particles within an oil. The significance of knowing that distribution is that we're suspecting most of it is going to be contamination. And if it's contamination, we can generally, filter it out and prevent any further wear that might occur from that. Or if it gets severe enough, we know whether or not to change the oil. Now, how is this test done? Well, again, give you an explanation on this one. So the way optical particle counting is done, and I put here that it's also known as laser particle counting, is that we take an intense source of light, so a laser, and we shine it through a moving thin film of sample. Now, on the other side of that thin film is a photodetector, not unlike the CCD detector in a digital camera. Now, as you maybe have heard this explanation before, what the detector is detecting are shadows. Now, a lot of people stop the explanation right there and don't tell you anything more about this because you pretty much think you can intuit what's being measured, right? By the size and shape of the shadow, you know the size and shape of the particle. It's like, well, yeah, sort of, but this instrument doesn't really care about the shape. What it's actually measuring is not a dimension of the shadow. It's not measuring the length or the width of the shadow. Because that's a common question I get asked is like when they say, well, what size is the particle? They go, well, is it the longest side, the shortest side, the average side? What is it? I go, sadly, it's none of those. And this is the part, again, not a lot of people realize. What particle counters and the optical particle counting style do is something called spherical equivalency. So what they do is they actually measure the area of the shadow. So you take a look at this particle here. It's 10 microns long by 1 micron wide. It doesn't take much math to figure out that's a 10 square micron shadow. But here's the interesting side of it. What it does is it assumes that particle is a sphere. And if that particle is a sphere, well, what shape is the shadow? Right? It's a circle. So what it does then is it tries to figure out what size circle would have the same area. So essentially, it's rendering your particle in its mind to look like this. So the area is unchanged, but the particle dimensions are vastly different. So then it basically reverse calculates this and says, oh, to get 10 square microns, that is a 3.6 micron particle. And here's the really scary thing about knowing this, now that you know that, is that the test only reports particles larger than 4. So that with a spherical equivalency of 4 microns or larger, that 10 by 1 particle actually goes unreported. So I think that's pretty interesting to note about optical particle counting is that one, it doesn't size the particles in the way that maybe you have assumed that they've been sized, but two, there are a significant number of particles that may go unreported because particle counting doesn't report anything smaller than 4 microns as a spherical equivalent. So that being said, just to quickly rattle off the same kind of things I talked about with the other one, what kind of limitations does this test have? Well, other than it won't report anything below 4 microns, it generally doesn't report anything larger than about 200 microns. And the only reason that limitation exists is literally the thickness of the film of oil that's being measured can't really accommodate particles that would measure out to be much larger than that. The other thing, though, and this is the important side of it, is to recognize right away that scale doesn't overlap very well with elemental spectroscopy. So you're already arriving at a bit of the short answer here is that I could have told you right at the beginning, why do my particle counting results not correlate with elemental spectroscopy? Well, essentially, they're not measuring the same particles at all. Even though it's the same oil sample being introduced, where they're targeting their analysis are two different ranges of size of the particles. But finishing off, anyways, optical particle counting, a quick little comment is for interferences. Something to note is that other things may give off shadows. So soft, like varnish particles, air bubbles, and water molecules can also cast a shadow on the photodetector unless the sample has been treated appropriately, which usually means we dilute it with a solvent to remove the effects of water and insolubles, and then we sonicate or vacuum it to get rid of the air bubbles. So a lot of sample prep is required for optical particle counting to approach some degree of accuracy. But that being said, this is one of two ways we can do a particle count. The other way is something, maybe you've heard of this before. Generally speaking, it's referred to as pore block, or some people call it the flow decay method. But the basic principle is much simpler. Essentially, we take your sample and we push it through a calibrated screen. So you've got a microscopic view of that screen on the right here with laser cut holes in it, all one size. And we push it through this screen at a constant pressure. On the back side of the screen, we measure the flow rate. And what's going to happen is that flow rate will decay. It will slow down as more and more holes in that screen get plugged with particles because the screen's essentially acting like a filter. Now, the important thing to note is that all the holes in the screen are one size. So typically 5, 10, or 15 microns is commonly used screens. And so say we're using a 10 micron screen. Well, what size particles are going to get stopped by a 10 micron screen? Well, anything that's got a dimension longer than 10 microns, it doesn't have to be wider than 10 microns, it has to be longer than 10 microns, and the particle will lay across that screen and not go through. Now, when that particle lays across the hole, does it block the whole hole? Not necessarily. So the holes begin to get smaller as particles start laying across that screen. So by the profile of the flow, so what we call the flow decay, how quickly it decays and how much it decays, gives us a way to extrapolate all the data regarding the particle sizes. So again, to be fair and upfront about this test, the limitation is it's not measuring every individual particle either. It's extrapolating the data about other particle sizes from a singular screen size. So, just again, trying to be fair. But what does this test have for interferences? Here's the best part. None. It doesn't care about air bubbles, soft varnish particles, or water. So to wrap this up here about particle counting, the big takeaway with this is, what are the limitations to a particle count? Well, it's really just a count, right? That's why it's called particle count. It didn't identify those particles in any way as to whether or not they were actually a wear metal, damage, or a contaminant, leading to damage. But the other big takeaway is that neither method is truly measuring every individual particle and not giving you a true physical dimension of that particle. It's only essentially relying on one method or the other, either spherical equivalency or just physical screen size at one particular micron rating. But the other takeaway that I put here is that you should expect that optical particle counting will report higher, skew higher than is the reality, which generally works in your favor, because if you can hit your target with a result that's skewed high, you're actually doing better than that. And poor block, the takeaway with this one is that it's been generally accepted that because of the way that the extrapolation is done, sort of the profile that's expected of flow decay, if you've got a very nonlinear distribution of particles because you've maybe got filtration in the range of one of the micron ratings that are being reported by particle count, it can sort of miss some of those particles because the profile, the flow decay won't match what the computer's expecting. So warts and all kind of presentation about both elemental spectroscopy and particle counting. But to kind of conclude us here, understand, and here's your short answer, they're not measuring the same particles. That's the key reason why two different tests aimed at measuring contamination and wear particles don't actually always correlate, is they're not measuring the same range, right? Elemental spectroscopy is focusing on particles smaller than 5 microns. It does get into a little bit of the 5 to 10 range, but not a whole lot of that can be considered accurate. Whereas particle counting is focusing on anything larger than 4 microns through either method that it's choosing to be reported at. The other thing that I put down here is understand that not all particles can be measured by both technologies. I give one example like soot. Soot is a very common form of particulate that you'll find, of course, in engine samples, but soot is comprised of carbon. We don't measure by elemental spectroscopy carbon because, well, the oil is made of carbon. So that wouldn't be very useful information. We get some very high results without really knowing which is the oil versus which is a contaminant. So things like soot can really skew a particle count and not show up at all in your elemental spectroscopy. But my other note here is, just emphasizing it's all about the size. The two tests really don't measure the same size particles, so what could you expect? But finishing us off here, the point is you should be able to see a correlation or a lack of correlation between those two results. So what if you see no correlation, right? A lot of people give up at this point because well, the two results aren't correlating. They're not telling me anything useful. It's like, no, sometimes the lack of correlation is very, very telling. So as I put here, what if your elemental spectroscopy results are high, but your particle count is low? Well, what that just confirmed to you is most of your particles are probably below around 5 microns. So that would tell you that they're usually normal-sized wear and normal-sized contaminant particles, the kind you expect. Now, if it's the other way around, if we flip this around and say, well, what if your elemental spectroscopy is low, but the particle count is actually high? Well, then you're probably dealing with a lot of larger than 5 micron particles, and that generally is expected to be more indicative of severe contamination, which ultimately leads to severe wear. Now, as I said, sometimes they don't correlate. Like both of these examples, they're not moving in the same direction. And like I said, there is something you can learn from that. There is something you can take away from that. But what happens if they do correlate? What happens if they are moving in the same direction? Well, that generally tells you that you've got particles on both sides of the equation here, that you've got particles that are both smaller than about 5 microns and a lot of particles that are larger than 5 microns. And that usually means that you're in that transitory period between normal wear and contamination and moving towards severe wear and contamination. So at the end of the day, there's still something you can learn either way from looking at the results. And I encourage you to, understand more, learn more about your oil analysis testing to understand what is truly being measured by the test. And that'll give you an idea as to what significance those results really have. And hopefully this is giving you an example that if you understand how the test is done, you can understand why the results will come out different from one test to another. And as I always jokingly say to people when they ask, how come there's two different tests for measuring the same thing? I say, because they don't see it the same way. And if they don't see it the same way, you're getting more information, right? And that's a common question that gets asked of other things like degradation or perhaps, insolubles and varnish testing. People are always wondering, why are there more than one test to do this? It's because they're seeing it from a different perspective. And that different perspective sometimes will correlate with your results and sometimes won't correlate. But in both cases, you're generally still learning something about that particular parameter. So, as I said at the very beginning of this presentation, the first limitation was the test selection. Obviously, I need to give you some idea. What is the next limitation? So the next limitation would be the accuracy of the test. And all I'll have to say about that is, well, that session is tomorrow. So, plug for myself to encourage you to join tomorrow's session, where I'm going to go through these same two tests again, but discuss the accuracy of these tests to let you know just how closely you should read into the data, because that's another common mistake that I come across all the time is people reading the data a little bit too far and seeing a little bit of a change and going, oh my goodness, it must be something catastrophic. And, once you learn about the test, you're like, that's just error within the method, noise on the instrument, don't care about that. Versus other times people ignore a change and think, well, this test varies a little bit. And you're like, no, that's a real change. That's a real issue. So that's my plug for tomorrow anyways, for sort of the second part of this presentation. But with that, I will end at this moment here and turn it over to if there's been any questions you'd like to ask. Definitely thank you for taking the time to watch this presentation, and hopefully you learned something.
Oh, appreciate it, Evan. Hey, you might have noticed Mr. Livingston has given you a new title. Now you're the analogy guru as well. Your counting stars analogy. I do have one quick question. Do labs typically, let me put it up on the screen, do labs typically have capability to run both tests?
Yeah, almost all commercial labs run elemental spectroscopy as a routine test, meaning like literally every sample that comes through the door gets elemental spectroscopy. And they almost all, I would be shocked if they didn't have a way of doing particle counting. Now, if you were referring, do they have the capability of doing both methods of particle counting? Then I would say the answer is probably less. Less labs have that ability to do both particle count tests. And partly it becomes whether or not they have the equipment for it. Not all labs have pore blockage particle counters. Almost every lab has optical particle counting as their primary technology. But something to note is even the labs that do have optical particle counting, not all of them run it on all samples. Some of the dirtier type of samples like engine oils and gear oils, some labs won't run particle count on those oils, or particularly viscous oil samples, some labs don't run. So it's a good question to ask the lab that you're dealing with. Do you run, this type of particle counting, whether you want to do them pore block or optical, and is there ever a time you won't run it? We at TestOil, we run everything. We have ways around almost any hurdle, so we run everything.
We really appreciate it. They're giving me the hook. I appreciate the presentation. Look forward to tomorrow's as well. I appreciate everybody attending. We'll see you in the next session. Thank you, Evan.
Thank you.